Welcome everyone to this ice-warm webinar today with Peter Buss, Soil Moisture Sensors for greater insights into crop water soil dynamics. We're delighted to have you with us today, and there's many coming on board as we speak. We're glad that Peter has joined us also. My name's Trevor Pillar, National Partnership Manager at IceWarm. Well, there's a ton of things coming up down track. I won't spend time on them right now, just so that you can see there's 5 webinars coming up in the next month and a half, and 2 or 3 short courses from the Australian Water School run by IceWarm, and we commend them to you highly. Today's agenda: 25 minutes from Peter and 25 minutes Q&A open to you all to comment and discuss. Secondly, we're making a recording and we'll send that out to everyone. And lastly, as you log off, the feedback form will just come up automatically. If you can spend 1 minute and tick boxes and write stuff that tells us how to shape these webinars in the future, we'll be absolutely delighted. It doesn't have to be wonderful comments, just comments that can make our webinars better. There's a map of the people that have registered for today's webinar, and the numbers are growing. I can see on the screen as we speak. That's enough intro. I want to get straight to Peter Buss. He's from Sentek Pty Ltd and has had decades, as you can see there, from point number 1 with on-farm irrigation management. Person with this background, we are just so delighted to have on board today. Peter founded Sentek back in 1991, but has been doing a ton of things. You can see point 5 there, 80 countries use his technology and is regarded as a world leader in this field. I don't think I need to go through all of that. I won't do that, Peter. What I'd like to do is just say how glad we are you can join us today, Peter, for 25, 30 minutes, 40 minutes. And we are very looking forward to seeing what you have to say to us. Right over to you, Peter.
Thank you very much, Trevor, and I'd like to thank you and IceWarm for organizing this webinar. And I'd like to welcome all the people everywhere in the world right now listening to this. Okay, I'd like to take you into the exciting world of saltwater plant atmosphere dynamics. What does it mean? We basically have a hydrological cycle. You see it here on your screen. It's basically the water cycle, rain coming down, entering the soil, getting taken up by crops and transpiring it again, and it goes around and around and around. And there are a lot of attributes and variables you see encircled here that are of interest either to a agricultural researcher or a farm manager. For example, you know, how quickly our water and nutrients are taken up, when do I get to a critical point, how quickly does my water infiltrate, do I get any leaching of water below the roots and with that fertilizer, what's my water table situation, and so on and so on. And you think you would need a lot of sensors to measure all these separate variables. Let me tell you, it's much more easier than that. What we really have done is we combined two completely different technology. The eye under the ground, which is really a multi-sensor soil water probe, you see it here, and a normal weather station that gives you air temperature, obviously rainfall, and ETO. ETO is the evapotranspiration, so the atmospheric demand that the crop is subjected to. And what you will learn during this webinar is by the combination of these 2 technologies, you can actually decipher a lot of insights that are very critical for farming, for irrigated farming, and also for agricultural research. So let's start with the farmer. What does the irrigation farmer want to know? Well, his important questions are when to irrigate without causing plant stress, right? That's a $64 million question. And how much do I need to irrigate? Because these people don't want to push water and fertilizer below the roots where they're wasting water, electricity, and fertilizer. And also, if it's a large farm, where do I need to irrigate next? Where do these 2 questions apply? When and how much? So that's the farmer. The researcher, they want to know, for example, they want to identify plant stress days of different, for example, corn genotypes, and relate them to yield to breed a better variety. And also they want to look at comparing depths and different depths of root zones to see which one can take more water out of a soil compared to another one. What is the speed of water infiltration into a given soil type? Very important for pivot operations because you can adjust the speed of pivots not to get too much runoff. And you can also they also ask, how much water drainage losses and water recharge rates can occur under certain circumstances. So let's take a look at these questions, and let's take a look at how we can answer them. So we developed a soil moisture technology that actually amazingly looks at what the plants are doing. And I just explained that a little bit. You have the water user, which is the crop, or in this case, it's the tree. And you all know the water and nutrients get taken up by the roots. They go up what we call the xylem, right? And they end up in the leaf where they're getting transpired. Transpiration is really a cooling mechanism to keep the plant cool. So most of the water that you actually see going through a crop is to cool itself, okay? And the water reservoir, or the bank where the water comes from, is the soil. And what we thought is, we make this analogy here. We have a water user, that lady, and we got the water reservoir, which is the glass. How about if you put a ruler to the reservoir and see how quickly, right, the water user is taking water from the reservoir. So in other words, we measure the drinking speed. And this has opened a lot of insights that we were not aware of, just about 25 years ago. And that's what I want to share. So what we have in the ground is basically a multi-sensor soil moisture probe. It can be equipped for salinity as well. And so every 10 minutes, this thing comes alive and it measures day and night. So you get about 144 readings a day, a full day. And it measures at increments of every 10 centimeters in the soil type. So you get individual layers of water content, which is important, and you get the sum for the entire profile. And here we're looking at a typically summed soil water graph. We're looking at what is the total amount of water in 1 meter of soil, okay? And the numbers here on the left indicate that's in millimeters. So you can see, it's quite a heavy soil type, 335 millimeters in that soil type. Down here, we got time in days, and you see rises. And obviously, if you have other information like when people irrigated or you had rainfall events, it makes sense. It should go up, and it does, right? But what you probably haven't seen so far is when it actually goes down, when the moisture is being lost because plants are actually taking it up. You get this really interesting, I call it staircase effect, right? So you got a step and then a relatively flat part. Guess why? Yes, you guessed it. The flat part is during nighttime. No transpiration really occurs. During day, the plant comes on and takes some water, okay? And so we have not a line that goes straight down. No, we have activity during the day and less activity during night. There are some losses during night that goes through drainage. Somewhere in the sum of that profile, water is still percolating. Now, let's take a closer look, right? I indicated again day and night here. So the gray is the night time, and you see the daytime during the white. Take a look. How come we got different step heights? Like, well, again, you guessed it. On this day, we had less temperature, it was colder, less wind, less radiation because of a cloud cover, and the plants haven't been using as much water. The day before, completely opposite. No cloud cover, hot, windy. So crops basically react like ourselves. They respond to the atmospheric demand because they have to cool themselves, right? So the plant, or the soil water dynamics, as you can see, are a fantastic reflectance of what actually happens above ground, right? So I plotted here ET values. So just explain, ET is not extraterrestrial, but it means evapotranspiration. So transpiration is all the water that goes basically through the plant and is transpired as steam into the atmosphere, okay? Evaporation, in contrast, is the part of the water that evaporates directly from the leaf surface without ever being inside the plant or the soil surface. And for practical reason, people combine that as ET. So ET you can get from a weather station or weather bureau, and you see it matches very well here on hot days, big drinks, cooler days, small drinks, and on hot days, a big drink again, right? So that's good. But why is that useful? Well, you can actually identify the very onset of stress, right? Because this synchronization between ET and stepping only occurs under non-stress condition. So take a look here. We have nice steps on these 2 ET days, right? There you go, and there you go. And then the ET gets actually hotter. So you would expect a bigger step. But look here, the opposite has happened. The step has actually diminished. And then ET falls back the next day to pretty much the same amount, but we have a further diminishment of the daily drink by the crop. So why is that? Now, the crop is actually indicating us right at that point of that day, right here, right? It has reached the limit of extracting the same rate of water in comparison to the day before. That we call the onset of crop water stress. And, you know, we have, over the last 26 years, we have identified with many, many crops, many soil types in irrigation system. That is a very critical point for commercial irrigation management. Another important question is, how far do we need to irrigate? Excuse me, I'm just recovering from a cold. Now, here we have separated the information in separate depth levels, okay? So the lines are basically, the top is a 10 centimeter, followed by the blue 20, and so on. And again, we're using the staircase effect, or the commencement of the staircase effect, day and night, to indicate to us when roots have reached a certain depth level. You can see here before, we just have irrigation, drainage, and suddenly we see stepping, meaning, aha, the roots have got to this level and they start working. And a little bit later, they go to this depth level, and later to this depth level. That's neat, isn't it? You don't have to dig it up. You can actually watch soil water dynamics indicating to you where are the roots taking water and also how much they are taking from this depth level. And that's what some researchers have done in the US, right? They not only map the depths of roots throughout the growing season and basically put the water consumption curve over that season, but they also attributed how much water came from different depth levels, right? Like in this case here, the vegetative stage 12, we have 68% coming from 20 centimeter soil depths and 32 from 30, and you can see how that changes. Now, why is that important? If you grade a genotype, you know, that is bred for drought-tolerant condition, you want to make sure we have deep roots and they can take up a lot of water for longer from deeper levels, right? And here's a tool how you actually can identify and compare directly different genotypes on the same location. Back to commercial agriculture, the question is after when to irrigate, how much to irrigate, right? And the how much is basically related to, okay, where are my roots? You can see in this picture, roots only, the stepping only extends to the third level. There's no stepping here at the lower levels. And this irrigation that's in the blue oval only pushed water to the third level. Great. You know, no water wastage, no electricity wastage in overpumping, and most important, no fertilizer leaching, right? Well done. Look at the other 3 irrigations coming afterwards, right? They all go deeper, push water deeper. So we're losing water and we're losing fertilizer and we're wasting electricity. So what we really want to do is we want to do what we learned was a good event in this blue oval. It happened to be on the 8th of February. Now watch, I'm taking exactly the same data and I sum them up in what we call the sum graph, right? So exactly the same data now are a profile sum graph. And we find the 8th of February, and that's where we draw a line, and we call this line the full point. And the full point indicates when, you know, when irrigation is really optimal, when this moisture content touches the upper line, then it's a perfect irrigation. When it goes into the blue, we're irrigating too much. We're wasting water and fertilizer. And when it hits the red here, we're getting into stress. So it's like a traffic sign for farmers, you know, stay on this green band. Don't go there and don't go there because it's commercial loss for you. I mentioned speed of infiltration, right? This is a zoomed in irrigation event, and you can actually see at 10 o'clock in the morning, the water hit 10 centimeters, and you can see the progression of wetting fronts moving down, and it hits 80 centimeters by just after 4 o'clock in the afternoon. Very important to for pivot speed, because we can make sure we get the right depths of irrigation, no runoff, right? So it's really, really an important thing. If you're a hydrologist, or you want to show a farmer how much water they're actually wasting, you can place a sensor below the roots, like we've done here, and we can actually show them how much water is being lost from the soil profile. Okay, and visit fertilizer, and sometimes that could be quite an eye-opener. I don't know whether you have seen what happens when you have too much water. Now, surface or flood irrigation are still being used in the world in many countries. Now, whenever you flood, something really peculiar happens. You have these nice big steps here, but you see when you get the flood here coming and covering the crop, you're waterlogging the crop. You just push out all the air out of every single pore, and you just have water. Now, that's not very good for the breathing apparatus of the plant, and it's causing a lot of stress. And you can see that stress is demonstrated here by these very small steps, and it takes 7 days, right, until the plant actually recovers and has enough air back in the system to go back to the normal stepping, right? This waterlogging stress in Australia, in particular in cotton industry, can cause quite some damage. So people trying to avoid it. Okay, but it has never been really shown how that actually looks, right? So in our software, we can actually identify the number of stress days, either that we spent in waterlogging time up here. You can see this is another example using alfalfa or lucerne, and the drought stress. So it slips into the red and it slips into the blue. So add up these days and create a yield relationship, and that's what it looks like. And this is a very interesting example from USDA, United States Department of Agriculture, in Beltsville, where we grew corn on a big field, and there were different soil textures, and corn was running into stress earlier or later, depending on the soil water storage and their textures that were associated with them. So you can see number of stress days here, right, and yield. So no stress, 160 bushels, but you can see just a few days, just a few days, and you drop quite significantly. 15 days of stress, 50% yield loss. Again, we introduced this concept to a lot of breeders and saying, if you want to evaluate the yield potential of crops under drought conditions, here's another tool that you can use to do this. Let's switch to drip. Now, the wetting onion or the drip pattern is very important. You must get enough wetting onion to accommodate the roots that support a certain size of canopy. If it's too small, the dripper is too wide apart, you have trouble. So you can do it the way they do it here in Florida. They dig it up and they color the water, and you can see different treatments, different dripper spacing give you different results. Again, we can do that much more simpler now by placing 2 probes at a short distance in either close to the plant and away from the dripper, and suddenly we can actually see what happens to the wetting pattern in live. We can actually convert that either into still pictures or videos like you see here. So blue meaning there's a lot of moisture and the water is actually moving diagonal. On here on the right you have the fertigation. You see actually where the fertilizer is ending up in all of this, right? Again, this will become very important tools in the future because drip irrigation is taking over the world, but it's one of the big unknowns where what actually happens underground. Nobody really knows and really understands. Again, everybody looks for a textbook example of a wetting onion, but they don't exist. Like you see here, after an irrigation, this is the shape. The wetting pattern gets just 50 centimeters out from the emitter, and then there's no more moisture, and it has not a nice round, half-round shape, but it's quite different. This is the shape starting to look under stress. So in the future, we'll be able to actually identify shapes. So having more pixels to define actually the onset of stress and when the crop is into stress. So what does the technology look like? Just to give you a picture here, we're using multi-sensor probes, right? And they have a modem and a battery up in the top here built in. And every 3 hours or whatever you set it to, it beams up the data to the cloud, and you can receive the data on a phone or tablet or computer or wherever. The important thing is the multiplicity of sensors, right? And the regular logging of data. So data are logged every 10 minutes, for example, uploaded every 3 hours. So you have them. And then it goes to the cloud. And the first thing you can see is pretty much a map. And you see in this case, it's a pivot farm. You see immediately the status of your soil water. So you have just 2 pivots that are stressed. And you have pivots that have been watered or overwatered. They're blue, and the green is indicating they're just perfect. And here is a priority list. So that actually shows you what is next. So 2 already should be irrigated, but you can see these are the candidates coming up for irrigation. If you click on an icon, then basically we'll get you straight to a graph. That's what a graph looks like. You have the sum graph. Again, we use a sum graph to identify the onset of stress. We use a separate level graph to see where the roots are and how deep we push the irrigation, right? So these become very, very important to graphs. Again, depending on the grower and farmer, we can make different graphs for different purposes. We can keep it simple, or we can make it more complex, whatever the customer wishes. We even predict forward when the line of a critical threshold is being reached. Okay, and as I said, you can get that now on the phone or tablet anywhere wherever you've got internet access. Consultants are using the information to go through it. They make their comments, right? And when the grower looks at that, then the graph is basically massaged for them, ready to digest. And all these people have then to do is follow the advice and start the irrigation or stop the irrigation, whatever. So look, to sum it up, we are looking at the attributes and the variables of the hydrological cycle. And what you've learned so far is with just 2 technologies, soil moisture underground and a weather station above ground, we can estimate and measure daily crop water use. We can find the onset of water stress in plants. We can determine the effective root zone of plants. In actual fact, as they're growing and as they're changing, we can see that, and we can change the irrigation depths over the season accordingly. We can find the irrigation full point. We can get a handle on soil profile infiltration. As I mentioned, very important for pivots. We have drainage losses, and we can measure that. We can see when we have complete saturation. There's a water table, becomes a completely flat line because we can't push more water inside the system. And we can see and measure the duration of waterlogging in crops. And we can work on that to minimize that as much as we possibly can with surface and flood irrigations. And last but not least, we can get a better handle on soil wetting and drying patterns under drip irrigations, right? So a lot of these things were, nebulous sort of concepts in the 20 years ago when we did not have very frequent data to look at, But by combining weather and soil moisture data, it's quite amazing. I hope you agree that what we can find out. So look, I thank you very much for that, and I hope it was useful wherever you are, and I'm open now for questions.
Peter, that is absolutely fantastic. It's just ubiquitous with diagrams. You'd agree with me that the presentation is clear as it could be. I appreciate the work you've done in this area, Peter, not just in the work of the irrigation, but in presenting this. It's been fantastic. And look, there's a lot of people with us today, all over every state of Australia. And I noticed 13 countries registered, but in particular, I'd like to welcome Professor Ibrahim Hashimi in the University of Tehran in Iran. That's great that you're with us. Hoping you might have some colleagues with you in the room as well. So what we're going to do now is open it up to you all to ask questions. I see there's a few on the board already, but don't hesitate to click that raise your hand button, and by all means come on screen and and speak with us, we'd be really loving that. Give it more of a live feel about it as well. It's live anyway, but just have more people on screen would be great, rather than Peter and myself. All right, let's get underway with our first question from Damien Zammit. Peter, many growers, such as mango growers, speak of optimum conditions being where the plant experiences a small degree of stress. Is that within your green zone?
Yeah, Damien, it's a good question. It not only applies to mangoes and actually a lot of other fruit where you want to concentrate sugars and get more quality and taste out of it. You know, the viticultural industry is probably at the foremost. We employ something called RDI, which means regulated deficit irrigation. So what we're doing during cell division is we're making sure that we have enough water for cell division, so there's no limit in yield. But later, when the cell division stops and we have cell filling, right, we actually reduce the amount of water. So the green band, right, is taking a different shape. It's actually fatter at some stage and slimmer at another stage, right? If you're with me. So yeah, good question. The green band does not stay all the same. It also changes, and I haven't shown you this, with the depth of roots in a seasonal crop. Say potatoes, they start off with a shallow root system, and then the roots go deeper and deeper. So we actually have to increase the depth of irrigation. So the green band is fattening up during the middle of the season. But as roots are dying down in field crops towards the end of the season, the green band is slimming down again as well.
Great. Yeah, thanks a lot for that, Damien. Philip, as a CSIRO scientist in Tasmania, he's asking how much site-specific calibration of these sensors do you recommend for each depth?
Okay. Yeah, I know calibration is a hot topic. We spend a lot of time and energy to at least create a library for the major soil types. But the emphasis, and what I hope to show you in the seminar, is that we put much more emphasis on the dynamics rather than the absolute values. So obviously, if you're a CSIRO researcher and you want to work out water use, we recommend that you actually calibrate the sensors for site, and we allow you to actually have a calibration equation for every depth level. If you know, like you have a duplex soil, sand over clay, you can actually do that. But for 95% of the world market, right, we use soil water dynamics and we don't calibrate. But we have a default calibration that's actually part of the equipment as it's shipped. But if you know your soil type, say a clay, you can actually pick one of the clay calibration equations in the software and insert that, and then see whether it matches your field capacity permanent wilting point threshold, and align it much more. So you know that's what you can do.
Peter's from Grundfos in Adelaide, and he's asked, can these technologies be applied to a third world for small crop farmers looking to increase crop yield?
Yeah, exactly. That's what we're doing. I'm actually contracted by the FAO and IEA to go around the world and actually exactly do that. I work with very small farm holders, and you know we install it. I teach exactly the same principle that you just have seen on your screen, and you know I watch them how they learn that and actually you know start to save water, make their fertilizer more effective, don't waste water and don't waste electricity. So yes, it can be done. You don't always have to have the fancy technology with modems and you know internet. We got variable different products that basically from handheld portable devices to devices where you actually have to go in the field and download them yourself rather than you know sitting nice and comfy behind a desk. So we can cater for different parts of the world with that, you know, depending on what the situation is.
Yep. That must be a very challenging but rewarding sort of work. What sort of countries are you going to?
Well, I covered. I'm actually going to Jamaica in December. I've been in Panama and Costa Rica, in Turkey, in the Seychelles.
Fantastic.
Goodness me. In Malaysia and so on. And yeah, it's quite a host of countries.
It's great.
Yeah.
Obviously something that's in demand, and that's fantastic. Somebody's asking about PowerPoint slides. Yes, these PowerPoint slides will be made available as a secure PDF after the webinar is finished. We'll email to you with PowerPoint slides and with a video recording location of that, so that's all good. Dharma has asked, thanks for the interesting talk, Peter. Can we get some indication of the cost of these systems?
Yeah, look, I can only give you ballpark figures because depending on where you are in the world, you know, distributors put different margins on them. But let's say, you know, you can get very entry products that probably cost you $1,000, and you know the luxury fancy bits with modem and everything else, they go up to $2,000, $2,500, you know, dollars per probe. It also depends on the number of sensors you want, right, to do. But my best bet is go to our webpage and take a look at our distributors that we have in many countries, and you know, just write them an email and saying, you know, I'm interested in this particular thing, give me a costing, and you know, they would be happy to do this.
Yep. Thanks, Dharma. You're from University of Sydney, Western Sydney University. That was excellent. Philip has asked, is there a social aspect to this where you get communities of learning?
Yeah, that's actually what I'm trying to do with the smallholders. You know, I conduct seminars reviewing the data and get other people locally involved and actually set up maybe a local consultant that says, hey, this is good, and you know, I can get some equipment and actually can help my own farmers to progress further. So that's really what I'm trying to do. That for me is the ultimate outcome if I can achieve that. Yes, obviously we like to share as much information as we possibly can, but it is sometimes difficult because people you know, don't get it the first time, and you need to really hold their hand sometimes. And what works in Australia does not necessarily work in Sri Lanka or anywhere else in the world. You know, the best thing is to set local examples and involve the local population. And if you make it there, it's a run downhill from there on, basically.
Yep, that's great. Simon Knowles in Earthwise Services in South Australia has said that he's interested in comments on the practical application of ET-driven soil water balances used in high-value drip irrigation in conjunction with soil water monitoring. So some comments around that.
Okay. Yeah. I actually gave a talk in the States where I looked at an ET modeling, decision-driven management plan for alfalfa here in Australia, and it completely ran off the rails because during the water stress and the waterlogging periods, the ET modeling would not pick that up and, you know, forecast the water use that was actually not existent. So by combining what I showed you before, real drinks during the day, real crop water uses with ET, we can actually create KC factors or crop factors that allow for stress, right? In actual fact, our software, if you have ETO coming in from BOM or anywhere else, where we can actually calculate the KC factor on the run for every day. So that obviously you need to calibrate the site for that, and then you get a really good thing. So if you're interested, talk to us. No, I think that's where it will go. There will be not just one instrument in the ground. The future will see integration of different data sets to help out with the best management decision. And they will involve weather, they will involve plants, direct plant sensing, soil, water, and nutrients, but also the irrigation system health. That all will be integrated platforms for the future that, you know, like in a factory today, building cars, certainly it will go that way.
Yep. Peter mentioned that he was at a UN 2017 Unleashed program in Denmark. I don't know whether you've heard of that, Peter, but he'd be keen to see some connections happening between them.
No, I haven't heard of that. So please contact us. Yeah, fantastic.
So we'll give everybody today here Peter's contact details. Is that a good idea, Peter, or come through us or something?
Yeah, you can come through. Yeah,
sure. Yep, no worries at all. That's great. Last question on the board right now. So we're going to wrap this up pretty soon. Simon said, "Thanks, Peter. Agree with your comments. I'm doing a project that will be doing just this, generating custom KCs for specific varieties with guidance with EnviroScan."
Okay, Simon. Yeah, I think if that's the Simon Knowles, I know.
That's one. Yep.
Hello. Good to hear from you. Now, exactly. Simon, you're probably not aware about the latest version of the desktop program. Basically, all you need really to do is get the ETO data in there. And obviously, if you calibrate for that soil type, then you get very accurate crop water use values. And then you can do exactly that. You can generate KC factors for every condition, different plant densities, different fertilizer regimes, different varieties, different crop heights, crop stages, even disease, or as I said before, stress, be it waterlogging. But you know the KC for that particular day, and I think that's a good thing forward.
There's a question from Lee Thompson, and I think you're coming on screen, Lee. Can you do that? Looks like you might be. Oh, I can hear you. That's all right. Speak up.
It's already been answered. Thank you very much.
Oh, that's okay. Thank you for coming on board. That's great. Yep. No, that's okay. Terrific. Already been answered. That's terrific. All right. Well, I think we're there. Any closing comments from you, Peter? When we'll wrap this up. It's been a very good time.
Again, Icebomb, thank you very much for the opportunity. And I know there's a lot of stuff to digest, and there's actually a lot of more interesting stuff. So if anybody of you is interested, maybe Trevor, you can distribute my email. I'm more than happy to enter in contacts, because people have certain projects and say, can you do this? Can you do that? So please feel free to ask questions. It's not a dumb question. Please ask, and we may be able to really help you and with something that you were not aware of, and you say, gee, I wish I would have known that before I started this particular project.
This is such a critical topic, and we're so delighted that you could join us today, Peter. The food-water nexus is not going to go away. The world population is telling that story, and we think we're onto something here. I think this is a really good direction to be going. Automating all that's fantastic. All right. Well, look, just to finish now, I'd just like to point out that there are a few webinars coming up. Don't forget to do the feedback form. That's the main thing. As this closes down in a moment, you'll get an automatic feedback form come up. We'll be recording it, and we'll email you that link along with the PowerPoint. And there's the new free webinars coming up there. Water Reforms Next with Professor John Williams. You'll be loving to hear what he's got to say. He's thinking it might look like a little bit like energy reform, and that's going to mean we're going to need some serious help. Won't go any more about that. Just to say how much we appreciate your time today, Peter, and thank you everyone for being on board. We kept most people with us for the entire time, so it must have been fairly interesting. It was for me anyway. Thanks very much, Peter. I hope we can do this again in the near future. Bye, everybody. Thank you for coming.
Bye-bye.
Bye.